Okay, we need to finish up section 10.1, then we need to do section 10.2. 10.2 kind of puts everything together. That's the final culmination of everything that we've done, section 10.2. 10.3 is just a little addendum, and it takes me about 15 minutes to cover 10.3. 10.2 is a big deal. Okay, so let's finish 10.1 before we even get there. We have to introduce this notion called a rank of a matrix. It makes it sound like it smells bad, but it's a different version of the word rank. It's more like a ranking system. That's the word rank that you want to think of. Okay, so I'm going to change your thinking. Okay, so far what we've had, matrices have been, in this class we've seen them in a couple different forms. First of all, we use them as a tool to study systems of equations. You got a system of equations, we could take the coefficients and put them in a matrix. So that's just a tool to get the job done. Then we stopped and we studied matrices as a mathematical object. We could add them, we could multiply them, we could find the inverse, we could do a bunch of different things with the matrix. We could manipulate them, do row operations and so forth. Now what I want to do is I want to tell you that a matrix is actually a function. So you're used to functions being f of x equals x squared or something like that, and believe me, we'll study that in detail in the second part of this class when we do the calculus. But for right now, we want to, this is the culmination. We finally say, okay, we've studied these matrices, and what's really going on behind the scenes is that these are functions. Okay, but we couldn't talk about them being functions because I couldn't say what their domain and range was. So I had to stop and go and talk about vector spaces because those are the domains and ranges. So let's start to change your thinking a little bit. Okay, so matrices, if we just choose to view them that way, they can be viewed as functions between vector spaces. They're not just functions though, they're linear transformations. That's the word, okay, linear transformations. But we don't really, you could spend a whole course talking about linear transformations. It's a big topic. So just to simplify it, we'll just say they're functions for our purposes. But they are linear. That's the thing to think of. Okay, so let's have a little example of this. It's already a little bit abstract. So A, if I give you a matrix A, okay, there it is. Now I'm telling you that this is a function. Right now it's just a matrix, but now we're going to choose to look at it in the form where it is a function. So how is that? Okay, well, if it's going to be a function, I need to have things that I put into the function. Like f of x, you take x and you put it into f of x, right? And that's the input. So what are the inputs of this function? Well, they're going to be little vectors because they come from the vector spaces. I'll set all this up in a minute, but I just want to get a few pieces of it up on the board. Okay, so there's a vector, and now what's going to happen is through multiplication, that's going to send this vector to another vector. Okay, so let's look at what happens. If I do A, V, well, that's just multiplication of two matrices. This one is a matrix, but we call it a vector. Okay, so here's the matrix multiplication setup. That's nothing new. When I do this multiplication, the first one I get, if I put the 1, 2, 1 on its side there, I get 0 for the first component. And then I get 1 plus 2 plus 0 is 3. So let's visualize what this is. This guy started off where? It's got 3 components, so it started off in R3. So the domain of this is R3. So you can write this like this. A is a function from R3, and where does it land? Well, whenever I do this multiplication, I always end up with only 2 components, so it can't land in R3. It lands in R2. We can do a little picture of this. Maybe I'll do it here. Okay, so here's Here's R3, and I just took a vector in R3. Okay, well, what are the components of the vector? Let's label the axes. This is x, y, z. Okay, so here's the x coordinate, that's 1. And then the y coordinate is 2. So I go out there. So just down in the xy plane, I've got this little bit. And then I'm going to go up 1. That takes me up 1 to that location, and that's my vector. So that's what 1, 2, 1 looks like in R3. And then this function comes along and hits it, and it takes it over, and now it's going to land here. It lands in R2. And what was the result? It was 0, 3. So 0, 3 looks like this. And that was the result. So it's not very enlightening to do this because, okay, well, that's just one vector. How do I get a feel for what the whole graph is? Well, it's really hard to because we're going from 3-dimensional space to 2-dimensional space. A bunch of stuff happens along the way, and so you don't really know. Okay, so we want to try to get a handle on this. All this example is here for is to illustrate how complicated these graphs are. So what we're going to try to do is just get a little glimpse into what's going on with them. The first thing I'm going to do is I'm going to talk about just the intuition behind this. We're going to count dimensions is what we'll do. Okay. I want you to notice a couple of things. First of all, A always sends 0 to 0. So think about that. If I put 0, 0, 0 here, so that's the 0 vector in this space here. If I put 0, 0, 0 here, I'm going to multiply by 0, 0, 0, and then what am I going to get? I'm going to get 0, 0. So if I have a bunch of zeros here, the only thing I get over here is zeros. So it kind of gives us a landmark. So in this case, we had A is from R3 to R2, but at least we know one spot got fixed. So here, let's draw the 3-dimensional version. There's the origin here, and then I go over here, A sends that to 0 here. But other vectors don't get sent to 0 necessarily. I mean, this one got sent from there to there, so it's hard to get a handle on the overall graph, but at least this one thing gives you a little landmark. Okay? Linear transformations send 0 to 0, or these matrices do. Okay, so I'm just going to go through a series of examples to show you the possibilities that can come up. Okay, so let's say I have A, and now I'm going from R2 to R2. So just picture that. Here's the symbolism, and if you hover over it with your mouse, right, you could see this picture. Right, and there's the origin. And if you hover over with your mouse, you'll see that picture. And A is going from here to here. So what are the possibilities? There are 3 possibilities. So the first thing let's just count dimensions. This 2 here, that represents the number of dimensions in the vector space. So you can say that this is 2-dimensional, and this is 2D as well. But what we're interested in, we're going to take this whole space, and then the result over here. Well, what if A was just the 0 matrix? Then what would be all the things that ended up graphing to? If A was the 0 matrix, just pretend that it has all zeros here. If it has all zeros here, then you're going to, any vector I take here is just going to give you 0 back, right? I won't be able to get away from 0. So that's one possibility, is I'm taking this whole space, which is two-dimensional, and one possibility is the outcome is just the single point 0. So you can think of it as it takes the whole space and it just smashes it down to 1 point. Every single point goes to 0. Okay, so this is not very interesting because it's the only outcome is 0, but this is the first step in understanding what can happen with these maps. Okay, this one here, we're going to say this one has rank 0. That is your first exposure to that term rank. And the way to think of rank 0 is the image of this graph has a zero-dimensional space, a point. Okay, the next possibility is, well, what's 1 up from 0 dimensions? That'd be 1 dimension, right? That's the next dimension up. And what is 1 dimension in this context? It's a line. But it's got to go through the origin. Because remember, the graph always takes 0 to 0. So no matter what, it's going to take this 0 to this 0. But it might take this whole space to just a single line. And this we're going to call rank 1. So as you build up, you just get a higher and higher rank. This is like a rank in the military or a ranking system. There's a hierarchy going on here. And then the third possibility, I should label these. Oh, let me just put it here since it's in order here. So I have the first one, the second one, and then the last one would be where I take this guy and it ends up giving you the whole space. That's right. We had rank 0, 1, and 2, and that's the largest I could ever have because it's a two-dimensional space that it's arriving at. So here I take the whole space and I arrive at the whole space. That doesn't mean it doesn't do other things to it. I don't want you to think that this just sends it exactly the same way. That's why I draw these one way and I didn't do it, but you should draw them like this so you don't think that it's it might rotate it, right? If you rotate it, the origin could still stay at 0. So that might be your linear transformation, is that it rotates it. This is what we call rank 2. So the idea, your first exposure to the rank is that it's the dimension of the image of this function. And in this case, if we had r was from r2 to r2, there's only 3 possibilities. You could either have dimension 0, dimension 1, or dimension 2. I can't have dimension 3 if the space I'm arriving at doesn't even have 3 dimensions. Okay, so that's your first one. Let's do a couple more of these just so you start to see the possibilities. Then ultimately what we're going to want to do is learn how to calculate this rank algebraically. I give you a matrix, I say what's the rank, then you go calculate it. Okay, what if we have A, which was from 2 dimensions into 3 dimensions? What are the possibilities? So here I'm taking my 2-dimensional space, R2, and I'm going into 3-dimensional space. It's always going to send the origin to the origin. And what are the possibilities? Again, we have 3 possibilities. We're going to have this guy get sent, oops, it's 3 dimensions. So we have the same possibilities as we have over there, except that each one of these has to land in 3 space. So we're going to have a rank 0 example. And this is rank 0. It sends everything to the origin. The image is just a single point which has 0 dimensions. Then we could have the possibility where, just like over here, it could have sent the 2-dimensional space into a line. But now our line is in this 3-dimensional space. So I might want to draw it like that. So everything here gets mapped down to one line. So that's rank 1. So before I write it up there, why don't you ask yourself, what would rank 2 be in this context? See if you can make that jump there. Okay, rank 2 over here is I take the two-dimensional space and my image is a two-dimensional space. Here, I'm going to start with a two-dimensional space. But I still have to land in the 3 space. But if it's going to be rank 2, the image is going to have dimension 2. And so what does that look like? That looks like a plane within the 3 dimensions. And again, I put there that the origin has to get sent to the origin. So it really does take this thing here, and it just puts it in 3 space as a plane. That's rank 2. And you can play games with this a lot. You know, you can sit there and set up the dimensions and do the different pictures. I'm just trying to give you an intuition for what rank really is. It's the dimension of the image that you end up with under these transformations. Let's go backwards. Let's do A is now going from 3 space into 2 space. What are the possibilities here? Well, here I'm starting off in 3 space and I'm going and I'm landing in 2. This is like the original example I gave you. Well, what are the possibilities? Well, I can only have 2 dimensions over here. So I could have the point, I could have the line, or I could have the whole space. So it's again those 3 possibilities. This guy can go over to just a single point. That's rank 0. It could go over to a single line. I'll put those in yellow. I put the line in yellow so it's distinct from its axes here. So this is a rank 1. And then we could have the whole space get mapped over to the whole 2 dimensions. And that would be rank 2. Now, one of the things I want to try to develop for you is this intuition. So you see, this is 3 dimensions. And then I land in 2 dimensions. So what has to happen to that last dimension? Where does it go? Something happened. Okay, I've got 3 dimensions here, and then I map everything over to 2 dimensions. So just ask yourself in your mind, what happened? What happens when we lose a dimension? Where does it go? Well, the answer is one of those dimensions goes to the origin. Everything gets smashed down to the origin. There's always one, whatever the extra dimension is, it has to get sent to 0. That's the way it works. This is a big subject, so you could take a whole class on this. I'm just trying to do a little sketch of what's going on here. That way at least you have a picture in your mind when you're looking at this stuff. Okay, let's just do one more. Let's do the possibilities where we have 3-dimension going into 3-dimension. So if I have A is from R3 to R3, then what we're talking about here is 3 dimensions going to 3 dimensions. So I've got an extra possibility here. So here I have 4 possibilities. Could have the rank 0, rank 1, rank 2, and now rank 3, because the potential for the image is 3-dimensional. So that biggest rank you could have is 3, and so now I have to have 0, 1, 2, and 3 as my possibilities. Okay, once again, it always takes the origin to the origin. So I could have the one where it sends the whole space into just the origin. If you like, I haven't been doing that. I could make that yellow, but anyway. So this is rank 0. And then I could have rank 1. That would be where I I get a line there in 3 space. And then we could have rank 2. Okay, what's rank 2? That means the dimension of the image has to be 2-dimensional, so that's a plane. And again, it takes the origin to the origin. So there's rank 2. And then rank 3 will be, it just takes the whole 3 space, the 3-dimensional space, into a 3-dimensional space. It might do some things along the way, but the result is a 3-dimensional image. If you want, you can kind of fill that in. We're talking about the whole thing, and then the result is, even though it sends 0 to 0, it might rotate things around or do some things. It's not just sending it exactly to itself. So those are the 4 possibilities for that one. You can't really do 4 dimensions because you can't draw it. So that's why we stop here and just get the intuition. But the same idea holds for, you know, something from R7 to R3. You have all these different possibilities. So what we want to be able to do is, from the matrix, detect what's going on here, which one of these things we're in, which one of the possibilities we're in, algebraically, just from looking at the matrix without having to graph anything or do anything like that. So that comes down to looking at the matrix and then finding out the number of rows that are linearly independent. That is the method that we're going to use. Let me write that down. So what we need is an algebraic way to determine the rank of a matrix. So what the rank is, just sort of intuitively, is it's the dimension of the image of the matrix A. And that doesn't quite tell you how to do it yet, but once we know that, then the way we find that is it's the number of linearly independent rows. And technically it's columns too, but since we do everything with rows, we'll just stick to the rows. Okay? We'll just do everything consistent with what we've been doing before. Okay, so then you're probably scratching your head, okay, well great, how do we find the number of linearly independent rows? Well, it's going to be something that we've done before. What are we going to do? We're going to take the matrix and we're going to reduce it to row echelon form. We reduce it to row echelon form, then we can just look at it and say, oh, the number of rows that are independent are the number of rows that are still there. And then we can say exactly what the rank is. So this rank idea, discovering what the rank of a matrix is, basically just boils down to reducing it to row echelon form, which is something we already know. It's just we're adding this new concept. It's a new application of the row reduction. So to find the rank of A, this is your recipe to find this. Reduce A to row echelon form. And count the number of non-zero rows. So that's easy enough, right? That's an old trick that you knew already, reducing matrices. So if you can reduce it and then you can count, then you can find the rank. And even if you don't know all this other stuff that's going on, you can still compute it and get the answer right. It's nice if you could get both, though, where you have a little intuition and you can do it algebraically. Okay, so let's take that original matrix that we had and let's find its rank. 1, 0, negative 1, 1, 1, 0. That's A. Okay, let's go find its rank. Well, what does it say to do? It says reduce A to row echelon form. Okay, so what does that mean? I need a leading one, and then it's the leading one here. I need to have only zeros in its column, so let's get rid of that. I'm going to reduce this by doing row 2 is replaced by negative row 1 plus row 2. I get 1, 0, negative 1. The first row doesn't change. The second row becomes 0, 1, negative 1, positive 1. And multiply this by negative, add it, I get 0. Multiply that by negative, add it, I get 1. Multiply that by negative, I add it, I get 1. And that is row reduced form. You see I've got this echelon formation, and all I need to have is I need to have the echelon formation together with the leading ones have only zeros in its column. So you see here's a leading one, only zeros in its column other than that. Here's a leading one, only zeros. The rest is... So this is an issue that you guys have when you're new to this, is when do you stop? How do you know you're in row echelon form? So that's what I just said. You can just make sure that the leading ones only have zeros elsewhere in the column. But also, if you were to try to make these zeros, you're going to ruin those zeros. That's another way you know to stop. If I want to get rid of this and I add those, I'm going to ruin that 0. So you're done. That's as far as you can go. Okay, so once I've got it in row echelon form, it says count the number of non-zero rows. Here there's 2. So that means the rank of A is 2. And the picture that now that we know the rank of A is 2, that means it's taking 3 dimensions into 2 dimensions, and it fills it all up. That's the case we're in, okay? The rank 2 case. Does anybody remember what the determinant of that matrix was? I did it in class. I mean, the only reason I think you might remember is because it's kind of an easy matrix to remember. But you might remember that we got 0 for that matrix, the determinant of that. So the determinant plays a role in this rank issue. And we're not going to spend a whole lot of time focusing on it. But the idea is if the determinant's 0, that means you lost a dimension along the way. Okay, that's another way to think of it. Okay, if the determinant is 0, you lose a dimension, or at least one. All right, so let's calculate the rank of A. All right, well, this one's a little bit worse than the last one because I have more numbers and no zeros to play with. But I'm going to take that upper left-hand corner as my pivot and just start making some zeros. Okay, so the first thing I'm going to do is I'm going to do replace row 2 with negative 4 row 1 plus row 2. And I'm going to replace row 3 with negative 7 row 1 plus row 3. Just doing row reduction. Okay, the top row doesn't change, so just reproduce it. And I know that these are going to become 0. You can put those in. That was by design. Now what happens? Let's do the second row. So I have the second row, I'm multiplying negative 4 times the negative 2. That makes negative 8. And add it, I get negative 3 here. Then I multiply by negative 4 here. I get negative 12. And add it, I get negative 6. Okay, then let's do row 3. I'm multiplying by negative 7 and adding it. Negative 7 gives me negative 14. Add that, I get negative 6. Multiply this by negative 7. That's negative 21. add 9, I get negative 12. So that's after your first step, and then we're trying to get row echelon form, so what do I need? If this is my first one, I need this to be a 1 here. So let's do that. I'm going to multiply, I'm going to do 2 steps here. I'm going to multiply row 2 by negative 1/3. And then I'm going to multiply row 3 by negative 1/6. So I have 1, 2, 3, 0, 1, 1, so 0, 2, 1, 2, and then 0, 1, 2. Okay, so now we're almost there. I'm going to, you see these are the same here? So I'm going to do 2 steps here. I'm going to do replace row 3 with negative row 2 plus row 3. And then I'm also going to get rid of this 2 here, because that's what you do with leading ones. This is going to be my next leading one. I need to make sure it doesn't have any zeros in its column. Okay, so I'm going to do negative, I'm going to replace row 1 with negative 2 row 2 plus row 1. 0, 1, 2, 0, 0, 0. That last row just becomes all zeros. And then the top row becomes 1, 0. Then I'm multiplying that by negative 2 and adding it, so I get a negative 1 there. Okay, and then what is it? I'm done. That's reduced row echelon form. It's got the echelon structure. Each leading one only has zeros in its column, and any row of zeros is in the bottom. That's the way we write the rows of 0. Okay, so I say that I've got 2 non-zero rows, so the rank of A is 2. Okay, I'll give you one to practice yourself. I'm not going to do the whole thing. I'm not going to do any of it. So A is 4 by 3. This is just a good one to practice for the midterm. I'll tell you the answer. So that rank is 3. Okay, so practice reducing that. Okay, we're going to do a little theory now, and this is, yes?
How come you didn't turn the third row, the bottom right coordinate, into a 1? Why did you stop there?
Because it turned out to be a row of zeros. When I went, see, my whole goal was to just get rid of this 1 here, but it turned out I also got rid of that. So there was no 1 to be had there. That's what caused it to have a lower rank. If we got a 1 here, then it would have had rank 3. Okay. So it's in this step. We just discovered it along the way. It doesn't always happen like this. It is possible that you would get a 1 there. Then it would be rank 3, though. So the special case, if you look up here, that's a 3 by 4 matrix. So if you, when it's A is a 3 by 4, then you can say what the mapping is. A must be from R4 to R3. So how did I figure that out? Well, in order to do the multiplication, I'm going to multiply by something, right? But in order for that to work, when I do that multiplication, it's got to line up. So I've got to have 4 spots there. And then when I do that multiplication, what's going to happen? I'm going to do it 3 times. I'm going to get 3 little slots for the answer. And so that's going to give me the image space as being R3. So a special case is when you have a square matrix, like in the last example. That's a 3 by 3. So we're going to focus on that a little bit. So A is an n by n matrix, which means behind the scenes, if you choose to look at it that way, it's a function from R3 to R3, or Rn to Rn. But 3 is one of those examples. So now I'm going to write down some facts that are kind of useful about this. So let's suppose that the rank of A equals n. So that means it's the highest rank possible, right? That's a way of looking at that. In this case here, here's a 3 by 3, and we did not get a rank of 3. So it's sort of a lower rank, right? So if you have a rank of n, in other words, full rank, that's actually a term that they use, so this is full rank. Then what does that mean? Okay, now look back at how we calculated the rank. What does that mean? That means we reduced it, and we didn't get any rows of zeros, right? When we reduced this one, we got a row of 0, so it had a little bit less of a rank, because when we count the rows, this one doesn't count towards the rank. So if we got a full rank here, then that means that the reduced A has no rows of zeros. So we reduce it all the way down, and we don't get any rows of zeros. Now think about that. Okay, now I've got my reduced matrix. It doesn't have any rows of zeros. What's the determinant? Is there any way the determinant would be 0? It turns out, no, look at this example, what she was mentioning. If we got an extra 1 here, then the determinant would have been 1, right? But here, the determinant's 0. So when you have a full rank, when you end up with no rows of zeros, then that means that the determinant of A is not equal to 0. It's an implication you can make. So I'm just making a connection between, so there's a rank of A, it's the full rank, then the determinant isn't 0. And then that means this. If I take a vector, if I try to solve this equation, AV equals 0. Well, let me put one more thing on here before I put that one. So if the determinant's not 0, what does the determinant tell you? It tells you whether there's an inverse or not, right? So that means the A inverse exists. Anybody need to copy this for a second? Because I want to extend this down and use both panels. Can I erase this? Well, if the inverse exists, then if I want to solve this equation, since the inverse exists, then that means that V is equal to A inverse of 0, which is 0. So the only possibility for this equation is that V equals 0. So these are all equivalent things. Rank is full rank, determinant's not 0, inverse exists, and then this equation here only has one solution, namely 0. And we have a vocabulary word that we use to describe this. This is non-singular. So the word non-singular for a matrix implies all of these things simultaneously. It's vocabulary. Sometimes you need one, sometimes you just need that the inverse exists. Sometimes you just need that the determinant isn't zero. Sometimes you want to find the rank. It depends on which fact is useful for you, but this word implies all of these things. Okay, well, if there's non-singular, then there's going to be singular. And singular is going to be the opposite of all these. So I'm going to write all those up there. Okay, so if a rank of n, it's not equal to n, then it's less than it. That's the other possibility. So the rank of A is less than n. So that's this case here, where this was a 3 by 3, and the rank was 2. It wasn't 3. Well, then that means that when I reduce it, if it's less than n, that means I had to get a row of zeros. So the reduced A has a row of zeros, at least one row of zeros. And if it has at least one row of zeros, doesn't that mean the determinant's 0? It's the opposite of this. If it didn't have any rows of zeros, then the determinant's not 0. But if it does have a row of zeros, then the determinant's 0. So if the rank is slightly less, look at the determinant here. Isn't the determinant of that 0? Okay, so then that means what? That means the inverse doesn't exist. So it's the opposite of it existing, right? That's what the determinant determines for you, is whether or not the inverse exists. Okay, and then this last piece here, a v equals 0. Okay, here v was the 0 vector, is the only solution, and now this is going to mean that v not equal to 0. Let's write it this way. There is v not equal to 0, so that av equals 0. And then the word that we apply to that is singular. Really, this is serving as partially a review, just to remind you the connection between the inverse and the determinant. But also, this last fact here, we're going to use this in the next thing we do. This fact here, that if it's got rank less than n, then there's this v, so that av equals 0. And what that means is it's going to lose a dimension. So if it's full rank, it doesn't lose any dimensions. And if it's less than full rank, then something had to be sent to 0. Either a line or a plane or something. So it had to lose some dimensions along the way. And that's what this is really saying. Okay, so vocabulary. For instance, on an exam, I might give you a matrix and I'd just say, is it singular? This is a simple question. So what would you do to test it? You could do anything you want. You could, if I had already asked you to find the inverse of the matrix, then you've already found it, and then the inverse exists, then you'd say it's non-singular. Right? So you have all these different tests. But basically, you just take the determinant. The determinant tells you whether it's singular or not. Because if it's 0, then it's singular. And if it's not 0, then it's non-singular. All right, so now we're going to put it all together and do section 10.2. This is called the eigenvalue problem. This problem ends up having almost everything that we've done in this class in it. You've got solving systems of equations, you've got multiplying matrices, you've got all kinds of stuff. Okay, but we're not going to quite get to this yet. We have to do a little background stuff. Okay, the first thing is I'm going to tell you what an orthogonal matrix is. It's just added to your list. It's another special matrix. Got to tell you what it is, though. Otherwise, you're not born knowing what that means, right? But you might, before I tell you, what should it mean? What's an orthogonal matrix? Well, the word orthogonal means right angle, right? So what does it mean for a matrix to be orthogonal? I know what two vectors orthogonal means. It means they're perpendicular, but what about a matrix? Well, remember, within a matrix, each little column is a vector. So what this is going to mean is that the vectors in the column are orthogonal. And then it's going to mean something a little extra too, but I'll tell you now. Okay, so the columns of an orthogonal matrix have two properties. The first one is that the columns are orthogonal. That's where the word comes from. Each column is orthogonal to all others. We'll have an example in a second. And then the other feature is that each column has length 1. Those are our two features. So let me give you an example of an orthogonal matrix. They've got some nice features, but they also usually have some ugly features. So you'll see it now. And Q, this is our orthogonal matrix. We'll start with a 2 by 2. Okay, how about 1? Let's use the one I have here. 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2. That's an orthogonal matrix. So let's check and see that it has these properties. Let's call this, here's the columns. Let's call that U and V. So let's check that U and V are perpendicular. So U transpose V, that's equal to 1 over root 2, 1 over root 2 times negative 1 over root 2, 1 over root 2. Okay, yeah, when I do this multiplication, I get negative a half plus a half, which is 0. So they are orthogonal. So the first condition holds. And then the second condition is that each column has length 1. So let's check the length of U. How do we do that? We take the square root of the squares of the components. So I'm going to square 1 over root 2. That's equal to square root of a half plus a half, which is 1. Okay, and then same with V. That's going to be, here I have negative a half, but it doesn't matter because I'm going to square it anyway. It's negative a half squared plus 1/2 squared. Oh, sorry, root 1 over root 2. That's equal to 1/2 plus 1/2, which is also equal to 1. So it satisfies both those conditions. There's an orthogonal matrix for you to chew on for a little bit. There's more to the orthogonal matrix, so this is why I'm showing it to you. I'm going to show you some of the features of it. If I take Q and I take its transpose and I multiply them by each other, you get the identity. So it's a really special matrix, because what that says is that the transpose is actually its inverse. So that usually is not the case, right? Transpose is just switching the rows and the columns. Turns out with this kind of a matrix, if you just switch the rows and columns, you end up with its inverse. And it doesn't matter which order you do this either. They're the same. So this statement here, we can verify it, and we will in a second, but this statement here, that implies, or another way of saying that, is that Q transpose is equal to Q inverse. So that's a really special matrix. It's going to make, it makes finding the inverse really easy, right? You can just write it down. You don't need to do any calculations. So orthogonal matrices have this property that the transpose is equal to the inverse. We can check that with ours there. So Q transpose Q. If I do the transpose, then the negative 1 over root 2 goes in the lower left-hand corner. 1 over root 2, negative 1 over root 2, and 1 over root 2, 1 over root 2. And I have 1 over root 2. I'll let you verify that that gives you the identity. But you can see, even just doing this one, you end up with a half plus a half is 1. Then you get a negative a half plus a positive a half is 0. Then you get negative plus positive is 0. And then you get positive a half plus positive a half is 1. Okay, so that's just verifying it, but this is the key fact. So now we're going to get into these transformations, these matrices as functions, and we're going to try to get a handle on what's going on inside of it. There's all this stuff that's going on behind the scenes inside of a matrix, and that's really what we're revealing here. It's like you have this blob of numbers, but if you look at it the right way, you can see the geometry that's going on inside, and that's what we're trying to get the training for, is to see some of that geometry. Okay, so we're ready for a big example here. And we'll develop this theory of eigenvalues and eigenvectors just using this example. And then next time we'll do some more examples. But we'll just beat this example to death. And you want to take the attitude with this that if you can't reproduce this example, then you have no business doing one that you've never seen before, right? If you can't even reproduce one you have seen before, why should you be trying one you haven't seen before? So there's a lot to do with this one, so I recommend being able to take a clean piece of paper and reproduce this example before you even move on to others. Okay, well, let's write this down as a function. It's a function from R2 to R2. I immediately can see that because I know this is a 2 by 2 matrix. Because there's a 2 and a 2, I got to have a 2 and a 2 there. Let's find out what this graph does. So one way to see it is let's take a look at the simplest basis that we've looked at before, the one where you have E1 and E2, where this guy here, this is 1 and this is 1. So E1 is equal to the vector 1, 0, and E2 is 0, 1. So this concept of basis, the way you want to think of it is these are the building blocks for this whole vector space, and if I use those as building blocks, then what it creates is this grid. So I can get to anywhere in that vector space using these two guys, and it's going to be on this little grid where every square has side equal to 1. So let's go over here and see what A does to that. What does A do to this? Well, let's do A of E1. That's equal to 2, 1, 1, 2 times 1, 0. That's equal to 2, 1. So A of E1, that's going to be 2, 1. And let's calculate the length of this too. What's the length of AE1? That's equal to square root of 2 squared plus 1 squared, which is root 5. So right away, let's just take a look at what happened to this one vector. It started off so nicely, all perpendicular to the y-axis. Then I hit it with this matrix, and it rotates it. It moves it from being here to here. It's like, think of it as a rotation if you want. But then it didn't just do that, because if it just rotated it, it would keep the length, right? But it rotated it, and it multiplied it by root 5, because it went from having length 1 to having root 5 length. So that transformation, just looking at that one vector, it rotates it a little bit, and it stretches it out a little. Let's take a look at the other one. If I have AE2, then that's 2, 1, 1, 2 times 0, 1. That's going to be 1, 2. Okay, so this is AE1, and then we get 1, 2. That's here. That's AE2. I'll make those yellow. So what has it done to that nice perpendicular grid that we had? It's given us this grid. So this is a line here, and this is a line, and then I can connect here and make that parallel, and connect here and make that parallel. So that's now what happened to our nice perpendicular grid under this map. It takes, you can imagine, it just skews everything. So even like a parabola here, if I had this little curve right here, it gets sent over to this curve right here. It stretches it out. So the reason I show you that is this is complicated. Okay, now the question is, are there any where it doesn't mess it up like this? Let's also calculate the length of E2. That's also equal to root 5. So what happened here, let me just write this down. What happened is not only did I rotate, but I also those vectors got longer. They got multiplied by root 5. A rotates and stretches R2. So here's the question. You see what's happening is there's a set of axes that A is operating on, and we don't know about it. We don't know. There is a set of perpendicular rectangles that A is operating on, and if we can find that, then we can see what A is really doing. See, this is not helpful because it takes what we're used to and it skews it in such a way that it's not going to give us a good picture of what's going on. So the question is, are there, and this goes back to, I guess I don't have, oh yeah, this is the eigenvalue problem. Are there any vectors in R2 that A doesn't rotate? You see, it's that rotation that's really messed up. That's what skews everything. So we're going to allow for the vector to get stretched out, but we're not going to allow for it to be rotated. This is what I want to find. I want to find the answer to this question. And it'll be yes always in our cases, because otherwise there's nothing to do. So, but then the question is, how do you find it? That's what we're doing. Okay, so let's write down what I mean by this pictorially. Okay, here's R2, and then A does its magic. So what I'm saying is, are there any vectors that it doesn't rotate? So if it doesn't rotate it, then there's going to be this vector v, and it doesn't rotate it, so I get the same angle, but it might be a little longer. So that's lambda v. Might get stretched out a little bit, but it didn't rotate. So in other words, it's the same vector, just has a different length, so it's in the same direction. So another way to think of this is this vector is sitting on a line, and this vector stays on that line. Okay, now if I can find two of these vectors, then what that's going to create is a set of axes for this matrix. And that's what we're really trying to find. So we need to start attacking this. So here's my goal. Given a matrix, so I hand you a matrix. In this case, it's always a square matrix. That's what we do with this problem doesn't apply to non-square matrices. So given A, n by n, find v not equal to 0 and lambda so that what has to happen? So algebraically, when I write this, I'm taking v, I multiply by a, so I get av, and that has to equal this. Okay, so I'm really trying to solve this equation. av equals lambda v. That's the eigenvalue problem. Are there any vectors where I hit it by a, and I get it back again, but it might just get modified slightly? By, think of this as being a 3 or a 2 or something. Lambda is a real number. Okay, so let's try to solve this. We have a little bit of experience with this. If I want to solve something like this, maybe that means AV minus lambda V equals 0. Right, just set it equals 0. And then I'm going to do one little extra step here. This is why they pay me the big bucks. Those are the same. And the justification for this step is I times V is equal to V. I is the identity. It acts like 1 in the matrix world. And the reason I did that, and we've seen this little trick before, the reason I did that is because I want to factor things out. I want to factor this V out. So let's do that. This implies that I have A minus lambda I times V equals 0. And here's where we use that little We're going to use those little factoids that I was talking about with rank here. This is the only place we use it. But I needed to have those facts available to me. Okay, so we're at this stage here, and we know that v is not equal to 0. So if you look back in the previous notes earlier in the class when I was talking about singular matrices, one of the features was that you have a matrix times a vector equals 0, and that vector is not 0. That means this is singular. So look back at what singular meant, and you'll see that that was equivalent to saying that that it had a vector, a non-zero vector, the matrix times that vector equals 0. That was one of the conditions. And then one of the other conditions was that the determinant is equal to 0. I'm just reminding you of the notation here. And this right here is what we're going to use to find what's called an eigenvalue. Okay, so let me okay, so eigenvalues of A, those are those lambdas. We're going to solve the determinant of A minus lambda I equals 0 for lambda. That's my first goal. Eventually, I'm going to go back and find out what this v is, but we'll talk about that in a second. So this is enough right here. Let's just go get the eigenvalues of a matrix by solving this equation. So A was that matrix, and I want to solve the determinant of A minus lambda I equals 0. And I'll tell you what that lambda is here. This is what's called the eigenvalue. Okay, so there's a couple of things going on here. First of all, we have A, so let's write that down. Let's get some numbers involved, right? Okay, there's A. Now, what about this guy here? What about lambda I? I, we know. I is the identity matrix. So this is A minus lambda times the identity matrix. And then the vertical lines here, that means I'm going to take the determinant of that once I figure out what the matrix actually is. And then I'm going to set that equal to 0. And notice the only variable involved here is lambda. So I'll be able to solve for lambda after I do all this. Okay, let's do a couple steps here. So this is the same as 2, 1, 1, 2 minus lambda 0, 0, lambda. Now, you don't have to write out all these steps. The first time through, I'm going to write them all out. But eventually, what you realize is all you're doing is subtracting lambda from the diagonal elements. You see, when I subtract this, I get 2 minus lambda on the upper left-hand corner. Then I get 1 minus 0, so that's just a 1 there. Then I get 1 minus 0 is 1. And then I have 2 minus lambda. So when you get good at this, what you realize is that to go from here, you go from here directly to this. Because all you're doing is you're just subtracting lambda from each diagonal. That's what you end up doing. But when I'm writing it out for the first time, just so you see all the little steps in all their glory. Okay, so we can take this determinant. What's the determinant here? It's AD minus BC, so that's 2 minus lambda squared minus 1 squared equals 0. So that's, let's multiply it out, or you can solve it however you want. let's just say 2 minus lambda squared equals 1. So 2 minus lambda is equal to plus or minus 1. So I have two possibilities. 2 minus lambda equals 1, and 2 minus lambda equals negative 1. Here, lambda is equal to 1, and here, lambda is equal to 3. Those are what you call the eigenvalues of A. Before we move on, let's go back and see what we were trying to do. Let's remind ourselves of the goal here. Okay, the goal was to find these vectors so that AV equals lambda V. Okay, but all we did was we found the lambda so far. We still have to go get these vectors. So there's two things that you're going to find. You're going to find what are called the eigenvalues, which we just did, and that's the complete solution. We've got the eigenvalues. Now that we have the eigenvalues, so now we can check this equation. We can say, okay, well, lambda equals 1. So I can put a 1 here. Then I put a 1 here. I just put a 1 for everything, and then now I can solve for V. So let's find out what V is. Now we need the eigenvectors. So for each value of lambda, find a vector so that AV equals lambda V. Okay, so let's just do a little bit of the algebra here. So that implies that AV minus lambda V equals 0, which means that A minus lambda I V equals 0. And we want to now solve this for V. So now we already know what lambda is. We have two cases. Lambda equals 1. Now I'm going to solve this with lambda equals 1. A minus 1 I V equals 0. What does that amount to? A minus 1I, that means subtracting 1 from, let's write it out. So this is 2, 1, 1, 2 minus lambda I is lambda 0, 0. There's V. This is my goal, to solve for this. I want to find out what this vector is. So that means I need to know what V1 is, and I need to know what V2 is. Okay, what about here? Lambda equals 1, so let's just put a 1 here. So now subtract those. I get 1, 1, 1, 1. V1, V2 equals 0, 0. So it now boils down to a little system of equations where I need to find those two little variables, V1 and V2. So I'm going to reproduce what my last step is there. My last step is, where is it? Yeah, 1, 1, 1, 1. So I have 1, 1, 1, 1, V1, V2 equals 0, 0. If I'm going to try to solve this system, let's put it in an augmented matrix. That's the same as this. And then I want to try to solve this system, and that'll give me the values V1 and V2. So what do we do here? Well, let's replace row 2 with negative row 1 plus row 2. And I get that. And by the way, if you see that the second row can be just canceled, when you're doing this in practice, you can just cross it off. You don't have to actually write out the other matrix, but I'm doing it for your notes. But sometimes you get pretty sick of writing matrices over and over again, so you want to develop a few shortcuts. Okay, so what are we going to do about this? This here says v1 plus v2 equals 0, which says that v2 is equal to negative v1. So what do we do? This takes us back to an old situation at the beginning of the course where we had underdetermined systems. What essentially happened is we lost one of the equations. So what happens is there's now infinitely many solutions. So let's write down our solution. I'm interested in v. v is equal to v1, v2. What have I found out about v1 and v2? What have I found out? Well, I found out that v2 is equal to minus v1, right? So let's just put that in. So I have v1, and then this is minus v1. So that's equal to v1, 1, negative 1. And you can consider this here is the eigenvector. If you like, let me just do that step another way. That's kind of the fastest way to do it. But to be consistent with how I did these problems before, what I'll do is I have v2 equals negative v1. What we could do is say set v1 equal to t, use a parameter, then that means v2 is equal to negative t. So then v is equal to v1, v2, that's equal to t, negative t, which is t times 1, negative 1. And that's the same vector I got out again. That's what's called the eigenvector. At this stage, there's lots of little tricks to get the eigenvector. So these are two ways to do it. Another way you could do this is you could just say set v1 equal to 1. If you set it equal to 1, then you just get 1, negative 1 immediately. But the reason I do this is to illustrate there's actually infinitely many of them. And it's a whole line. But we just want to get one of those. And there's the eigenvector. Now the good news, even though this was really complicated, the first time through it's really complicated, but we get to repeat it. Because for every eigenvalue, we get an eigenvector. So we get to see this process over and over again, and that'll help us get pretty fluent with the method. Okay, so what I just did is I did all that. I found the eigenvector for lambda equals 1. Or did I use 1? Yeah, I did. So for lambda equals 1, we got the eigenvector v is equal to 1, negative 1. And let's just check and see if that is in fact, our whole goal was to get a v equals lambda v. So let's see if it actually happened. So a v, that's equal to 2, 1, 1, 2 times 1, negative 1. That's v. And when I do that multiplication, I get 2 minus 1 is 1, and then 1 minus 2 is negative 1. And look, isn't that 1 times 1, negative 1? So AV is equal to, which is lambda v. So in fact, that is the eigenvalue and the eigenvector that solved that original equation. Let's go now and do the other eigenvalue. We'll do lambda equals 3. So let's just recap here. Okay, I start off with lambda equals 1, and then I went and I found the vector. So now I'm going to start off with lambda equals 3, and I want some vector, let's call it w, so that AW is equal to 3W. That's what I want. So I'm going to solve A minus 3I W equals 0. That's, I basically bring the 3W over here, factor out the W. This, when I do this, it's 2, 1, 1, 2 minus 3, 3, 0, 0 times W1, W2 equals 0, 0. And then this over here gives me negative 1, 1, 1, negative 1. Okay, so right now we're at the same stage. Where were we here? We're right at this stage right here. So here what we did was we took this and we put it in an augmented matrix. Then I used the augmented matrix to find out what the V1 and the V2 are. I'm going to do the same here. So right from this, I get 1, negative 1, 1, 1, negative 1, 0, 0. That's my augmented matrix. And I'll reduce that. Let's do, let's go down here. So what I'll do to get rid of the bottom row is I'm going to do replace row 2 with row 1 plus row 2. So now I get negative 1, 1, 0, 0, 0, 0. And then this guy here, this part of the process is very repetitive. So the first time through, you don't really know what's going on, but when you see it multiple times, you'll start to pick up the pattern. So this says that W1, negative W1 plus W2 equals 0, which then says that W2 is equal to W1. So now the vector I'm interested in, W, that's W1, W2. Well, I have another name for W2. I can just call it W1. And there's your eigenvector. That's your eigenvector. And you can check that. If I do AW, that's 2, 1, 1, 2. W is 1, 1. Look what happens when I do this multiplication. I get 3 on the top, and then I get 3 on the bottom. And that's 3 times 1, 1, which is lambda v. So in fact, we have found the eigenvector associated to that eigenvalue. Let's see, where do I want it? That's it for that side. Okay, let's kind of recap what we've got here. Our goal was to find these special vectors and the special values that go with those vectors. So let's recap what we got. We started off with A, and then we got 2 eigenvalues. And then for this eigenvalue, we got the vector v, which was 1, negative 1. And we got the vector for this guy over here, which was 1, or is it the other way around? This one was 1, 1, yeah. And these are the eigenvectors. So now what we're going to do is we're going to make a matrix out of this. What do we do with this information? We're going to take it and put it in a matrix. That's where we store information. Notice that V and W are perpendicular. Notice that V and W are perpendicular. I have a little picture I want to show you for this. So here's the picture. This is the real way to look at this, what this matrix is doing to R2. Is the way it's viewing it is it says I've got these special vectors that I'm operating on. So here's the first one, 1, 1. That's W, right? There's 1, 1. And then the other one was 1, negative 1. That was V. And so the way that that matrix is viewing the space is it views the space like this with this grid. That's the way it views the space. And now when you take this space and you map it over here, what does it do? It takes this vector and it multiplies it by 3. And it takes this vector and it just keeps it multiplied by 1. So all it does, when you look at it this way, it's not so confusing. It doesn't totally skew the space. If I look at it like this, let's put another grid here like that. If I look at it like that, then what happens is I end up with this over here. This one stays at length 1, but this guy goes to 3W. So now my new grid is like this. I don't want this one. I want them to have length 3. Okay, so it just takes this and it just kind of stretches it out a little bit. That's a much simpler way of looking at it. You can't know that from just looking at the matrix. You have to study this theory and discover it separately, and then you can go back and say, oh yeah, that's what's really going on, is that this matrix views the space this way. Then when it does the mapping, it just keeps it in that grid. And now we can kind of see what's going on when you view it that way. Okay, so that's the picture behind the scenes. Now one last step, we have to learn what to do with all this information. We're almost at the end here. I know it seems like a huge, well, it is a huge undertaking, because look at all the different things we're doing here. We have systems of equations, we have linear transformation theory, all kinds of stuff going on here. Determinants. Okay, so notice that V and W are orthogonal. So V transpose W, that's equal to 1, negative 1 times 1, 1. That's equal to 1 minus 1, which is 0. So V and W, and I drew the picture too. We can also see that from over here. Okay, and let's get the lengths of the vectors. Okay, what's the length of V? Well, the length of V will be the square root of 1 squared plus negative 1 squared, which is root 2. And the length of W, that's going to be 1 squared plus 1 squared, which is also root 2. So let me ask you something. If I take a vector and I want to, this vector has length root 2. What if I want it to have length 1? What should I do? If I have the number 5 and I want to make it have length 1, what do? I divide by 5, right? So if I have 7 and I want to make it have length 1, I divide by 7. So if I have a vector and I want it to have length 1, I divide by its length. So V over that is 1 over root 2 times 1 negative 1. which is 1 over root 2, negative 1 over root 2. And the length of that has length 1. So if I just divide a vector by its own length, I get what's called a unit vector. But anyway, if you divide a vector by its length, you get a vector of length 1. And same with this guy. This has length 1. All right, so here's what we're going to do. We're going to take those vectors and we're going to put them in a matrix. And that matrix is going to be orthogonal. And that's how we started off this section, as we talked about orthogonal matrices. So we're now tying it all together. I'm going to create Q. Okay, so Q, how am I going to create Q? I'm going to take my eigenvectors and I'm going to put them in there. But I'm not going to just take the original eigenvectors. I'm going to take, remember, an orthogonal matrix has to have the columns length 1. So I'm going to put in here U, did I call it? Yeah, V and W. There we go. V and W. Those are my two columns. So that's going to be, okay, what's V over its length? That's 1 over root 2 minus 1 over root 2. And then W over its length, that's 1 over root 2, 1 over root 2. So there's Q. Now Q is orthogonal. Which means that Q transpose equals Q inverse. That's the significance of being orthogonal. Okay, now here's the magic of everything we're doing here. We're going to take our original matrix A, and we're going to, it's like taking it and putting it in a distiller. It's got all this extra stuff, but I put it in a distiller, it melts away all the extra information, it gives you just the essence of the matrix. We're going to expose the essence of our original matrix 2, 1, 1, 2. If I multiply Q transpose A, Q, so what is that? Let's do that. Q transpose is 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2. And then A is 2, 1, 1, 2. And then Q is this right here, 1 over root 2, negative 1 over root 2. Okay, so that's 3 matrices to multiply together. Before we just jump right in and do that, let's see if we can make our lives a little easier. This is the same as 1 over root 2 times 1, negative 1, 1, 1, 2, 1, 1, 2, and then times 1 over root 2, 1, 1, negative 1, 1. See if you agree with that. All I did was just factor out the 1 over root 2, because it's so ugly, isn't it? Can we all agree that that's ugly? It is. And I don't really want to do any multiplication that involves that, if I can avoid it. Okay, so now I'm going to pull this 1 over root 2 and this 1 over root 2 together, and it just gives me a half. And then I'm going to keep this matrix, and I'm going to do this multiplication. I got to get some of this done now. Right, I got to get some of the multiplication done. So these two guys became the half. This guy stayed the same, and now I'm going to do this multiplication here. When I do that, I get 1 for the upper left-hand corner. Then I get negative 1. Then I get 2 minus 1 is 1. Oh, hold on here. Make sure I don't do this right. I had a little tick mark here. Okay, so this is 3 here. It's 1. It's 2 plus 1. And then I get 2 plus 1 again. Okay, now I'm going to do these two. When I multiply those two, I get 2 then I get 0, then I get 6, oh no, then I get 0, and then I get 6 for the last one. And so when I finish this off, what do I get when I multiply by a half? And these are the eigenvalues. Okay, so what I need to do right now is I need to go through and just recap everything that we've done, okay? Because we did a lot of things, and I was explaining it along the way. What we've essentially done here, I'll just tell you, and then I'm going to write all this out, and then we'll be done for the day. So I start off with A, and I multiplied it on either side of itself with this special matrix that I created. And how did I create that matrix? I used the eigenvectors. So I multiplied it on each side by that, and what did I get? I got a diagonal matrix, and that diagonal matrix has the eigenvalues of A. And so this is the essence of A. A behaves like this diagonal matrix when you view it in this context. If you look at it like this, what does it do? It multiplies this vector by 3, that's the 3 in the diagonal matrix, and it multiplies this vector by 1. So that's what we've discovered here. Now I need to just recap it, and that way you have a recipe for all this on one page. So like I said before, in order to really master this, you really need to just take this example and reproduce it, okay? And all the other examples are similar to this, so that's why this is a good place to start. Okay, we started off with a matrix. I give that to you. All the rest is done by you. And the goal here is, first, we're going to find the eigenvalues of A. Okay, now how do you do that? If you look back in the notes, you can find it, but we'll just recap it here. What we do is we solve the determinant of A minus lambda I equals 0. And you solve that for lambda. And that's your first step. Okay, finding the eigenvalues involves solving that equation. Then the next step is to find the eigenvectors. These are the vectors that go with each of those lambdas that you found in part 1. So for each, and I'm going to highlight that, for each value of lambda found in part 1, for each of those, notice we did it twice because we had lambda equals 1 and lambda equals 3, solve A minus lambda I equal V equals 0. So I'll just highlight here that maybe for your notes if it helps you, that these two things look similar, but here we're solving this for V, and here we're solving for lambda. Here we have vertical lines, that means take the determinant. Here we don't. Okay, there's no determinant here. So try to pay attention to the symbology there to help you remember what to do. Okay, step 3 is just to collect everything we have. So in our case, we had lambda equals 1, and then we got V equals 1, negative 1. And then we had, for lambda equals 3, we had W equals 1, 1. So those were our results of 1 and 2. Step 4 was to take those vectors and make them have length 1. So make vectors length 1, how? You divide by their current lengths. So we go v divided by its own length. In that case, we got 1 over root 2, negative 1 over root 2. And then we took w and divided by its own length. And so that gave us 1 over root 2, 1 over root 2. Next step was we took those, once we calculated them, we took them and we put them in a matrix. We created this Q. See what I did? I took these new vectors that I created with length 1 and I put them in a matrix. And that's the magic matrix. That's the one that changes A into that diagonal matrix. Okay, so let's put length 1 vectors from step 4 into here. Q, if you want, you can write them out. It's V over length of V, W over length of W. And that turned out to be this matrix here. I'll put it up above in a second. So then we put those length 1 vectors into, and we made this new matrix, and then that matrix is what caused this, what's called diagonalization. And we're almost there. So when you do this multiplication, now actually you don't have to do the multiplication because we're going to look at what the result, you see from this example, we can see what the result's going to be. The result is going to be a matrix with the eigenvalues in it. That's why I use this capital lambda. This is capital lambda. So that indicates that the eigenvalues are going to be in there. So what did we get here? This turned out to be 1, 0, 0, 3. Where those are the eigenvalues. And I want to also, so Q, I want to highlight this. So Q is equal to this matrix here. Where was it? Is it the one negative there? Yeah, okay. 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2. This is the one from V, and this is the one from W. So, okay, so what was the eigenvalue that went with V? That should be lambda equals 1, and this one was lambda equals 3. And so if you have V first, then lambda is first. And if you have W second, then W, the eigenvalue shows up second over there. So the reason I'm saying that is because you might choose when you make your Q, you might switch these two. I can't control that, right? You just had two vectors. You might have found this one first, so then you put that one in first. That's going to cause this to be switched, so they may match up. This guy goes with this guy. The first vector goes with the first eigenvalue. So QTAQ, the last is that this is what's called the diagonalized A. And essentially it's like the essence of A. A behaves like this matrix does when you look at that, rotated axis. Okay, so what you need to do is just sit there and go through each step here and first find the eigenvalues, practice that, then practice the eigenvectors, and once you get those two, everything's sort of mechanical. and you just put it in the matrix. And I also want to point out, I said this before, but I'll say it again. Notice here, when I did this multiplication, I got this answer, but you can just write the answer. Because if you know in advance that the thing you get is the matrix with the eigenvalues, then just put them in. You don't actually have to do the multiplication. So don't think you have to do that multiplication. If I ask you for the diagonalized matrix, you just give me the one with the eigenvalues in it. That's all. Okay, so you'll have, we'll do another full example of this, and it'll go much more quickly next time because I won't have to explain all the steps. I'll just give you a matrix and we'll just power through it, and you'll see that it's not so bad. So on Wednesday I'll do that. That'll be from your sample midterm. I'll have a question like this on there. So you'll get a chance to see it again. But I do recommend between now and Wednesday, try to practice this one. So if you could sit there with a clean piece of paper and reproduce the whole thing, you'd be really ready for Wednesday's lecture. Okay, let me get some questions from you if you have any. Too much to even have any questions, right? Okay, I get that. All right, maybe you'll have some questions on Wednesday, or maybe you'll have some questions for discussion section. Okay, that's it.